So today we are going to look at galaxies and their central engines, the black holes, the supermassive black holes that lie in the center of the galaxies. These black holes play a very important role in their formation as well as the activity throughout their lives. In the first bit, what I will do is I'll look at the supermassive black hole that is at the center of our own galaxy, the Milky Way, because it is very near us and we can get a very close look at it. As you remember, we looked at what our galaxy looks like. We can see that if we look at the galaxy sideways, you will find that it's a very flat disk and there is a lot of dust in the plane of the galaxy, and our sun is not situated at the very center of the galaxy. In the center, whatever is there is obscured by dust, as can be seen in optical images. Looking from the top, we can see that the galaxy looks like it has a bulge in the middle and has spiral arms around it. It is very difficult to look at the middle of the galaxy through conventional light. So our exercise now is to find out what is there in the middle of the galaxy. In order to look through this dust that is in the plane of the galaxy, one has to look at other wavelengths, not conventional light, which is absorbed by the dust in the plane of the galaxy, which is also abundant in the middle of the galaxy. Now, we now know that there is a central black hole in the middle of the galaxy of mass about 4 million times the mass of the Sun, and we are going to look at how we can find that and measure the mass of the galaxy. One of the ways to do it is to look at the motion of stars that are very close to the center of our galaxy. Just like in the solar system, we look at the motion of the planets around the Sun, and by looking at the distance from the Sun as well as their motion, we can measure the mass of the Sun. Just like that, in the center of the Milky Way, if we look at the stars and look at their orbits, we can try and measure the mass of the central object that is causing this motion. We can also put a limit on the size of this central object. Both are essential ingredients in establishing that there is a black hole in the middle of our galaxy, as well as measure its mass. So one of the things that we need to establish this is for a very different kind of telescopic observation. This is because if we want to look at the stars right near the middle of our galaxy, we need a resolution of much better than a second of arc, which is a normal kind of resolution of the telescopes that we use due to the turbulence of the atmosphere. To compensate for that, there is a new technology called adaptive optics, which changes the shape of a mirror or an assortment of mirrors in real time to compensate for atmospheric turbulence. And in doing so, it can increase the resolution because it compensates for what is known as atmospheric seeing, and it can turn an image that might have a point spread function of a few arc seconds into an image where the stars itself or the point objects have sizes of 1/10 of an arc second or better. We need this at the center of our galaxy because at the center of our galaxy, if we look at the stars, and this is a real picture of the stars around the center of our galaxy taken in the near infrared at 2.2 microns, you can see that here this entire image is about 1/2 of arc, and the sizes of the stars are much smaller, and without adaptive optics, this new technology, it would be very difficult to measure the orbits of individual objects. Here in the center of this image is the square is where we think the black hole in the middle of our galaxy is. Of course, we won't see the black hole, we won't see any light coming out of it, but we are going to take the stars that are around the central black hole and measure the orbits. And just like, as I said, in the solar system, we will use Kepler's laws, we'll find the mass of the black hole at the center of the galaxy. So here is an animation of the stars that lie at the center of our galaxy, taken from the Keck telescope. People have been observing the stars at the center of our galaxy from about 1995 up to now. So we have built up more than 20 years worth of observations using adaptive optics on the Keck telescope to find out the orbits of these individual stars. You can see the bar out here represents 1/10 of an arc second. So the resolution of these images are much better than 1/10 of the arc second, so we can see these individual stars. And in the animation of these stars, you will be seeing that we now in the 20 years have measured full orbits of many of these stars. The star called S2, which the orbit is in yellow, which has completed more than one orbit in this period. It has an orbit of about 11 years. And there are many others which have completed these orbits. All are elliptical orbits which have a common focus, which is given by where the center of our galaxy is, where this central object is. There are two groups that have been working on this. There's a group that works in Germany at the Max Planck Institute, Reinhard Genzel's group, who use the Very Large Telescope in Chile, in the southern hemisphere. And then there is the group at UCLA, led by Andrea Ghez, who use the Keck telescope in Hawaii to do the same thing. And they both use adaptive optics on very large telescopes, 8 to 10 meter class telescopes. And they both observe in the near infrared to get independently these orbits of the stars. This diagram, for example, is from the German group, and this is from the group at UCLA. And in both cases, what they have found from these orbits of stars that are marked S1, S2, etc., is that you can get an independent measure of the central object in the Milky Way from Kepler's laws. So what you do is, for example, S2 has an orbit of 15 years, and it has a eccentricity, a very large eccentricity, not like in the solar system. And even as early as 2002, as you can see, one could measure from the measurements that have been done every year the elliptical orbit that it is on, and we could see that its distance from the focus where the unknown object is about 120 AU. That's the distance of the sun, 120 times it, so it's a very small distance. Sorry, one could measure the distance, the closest distance that the star gets to from the central object, and one could use simple Kepler's third law to infer that the mass of the central object is 3.5 times 10 to the 6 solar masses. If you take that mass and convert it into a Schwarzschild radius, you would find that it would be something like 15 times the radius of the sun, which is about 8% of an AU. So it's very small compared to the nearest distance that the star goes to the central object. The central object, which is marked as Sagittarius A star there, even if it is a star cluster of this mass, which is possible, globular clusters have masses of 1,000,000 times the mass of the sun. If it is a star cluster, it would be at least a few parsecs in size, and so having a distance of close approach a few hundred AU rules out the presence of star clusters of that mass there. And the only kind of star, single star, that we can think of that can inhabit that particular focus would be a black hole of the mass which is very close to 4 times the 4 million times the mass of the Sun. Here is an animation that is inferred from these observations taken over the 20 years or so, but shown in 3D to show that one can even measure, of course, the velocities in real time. People have reconstructed the 3D orbits of the stars around the center of the Milky Way. So now shifting to the near infrared, here is an image taken by the Keck telescope of the galactic center at 2.2 microns, that's in the K band, where one can look through the dust in the center of the galaxy, and one can look at then the images of the stars around the center. Now here are two images, one with and one without the use of adaptive optics, and the central box in the middle of this image has a size of 1 arcsecond. And as you can see, without adaptive optics it is very difficult to make out the images of the individual stars there, whereas in the one with adaptive optics you can see the individual stars, and then these are repeatedly observed every few days to find their orbits. So not only does the Milky Way have a supermassive black hole in its core, we find that all large galaxies have one of these in the middle. In the case of the Milky Way, the mass of the central black hole we saw was a few times 10 to the power 6 times the mass of the Sun. Many other galaxies have even more massive black holes in the middle, going up all the way to 10 to the power 9 solar masses. Here are some early Hubble Space Telescope pictures of the central regions of galaxies, showing activity in the middle of galaxies. These are all powered by these supermassive black holes that lie in the middle of these galaxies. And these can be spirals, ellipticals, or irregulars. As long as it's a sufficiently large galaxy, one has evidence of supermassive black holes in their middle. Here is an example of a nearby elliptical, which is at the core of the Virgo cluster. It was very early on observed by the Hubble Space Telescope, looking at exquisite resolution in the middle of the galaxy, and one could, from the rotating gas in the center of the galaxy, find evidence of a central black hole in the middle, where the mass of this black hole is a few times 10 to the power 9 times the mass of the Sun. This is far more massive than the black hole that is in the middle of our galaxy. Looking at a spiral galaxy, for example, M106, one can look at the middle of this galaxy, which is very similar to our own galaxy. These galaxies sometimes around the center have maser sources, which can be picked up by radio telescopes, and these can be very accurately measured in their velocities. But the good thing about maser sources is that their positions, their distances also can be measured, and so one can build up a 3D orbit of these maser sources around the center of the galaxy. And by measuring the orbits of these maser sources in the middle of this nearby spiral galaxy, one has found that the mass of the central object is 3 times 10 to the 7 times the mass of the Sun. So this is even a factor of 10 almost more massive than the black hole in the center of our galaxy. Now, to establish the existence of these black holes in the middle, one has to find some way one has to find some way of measuring the mass, and one can use all kinds of techniques. I showed you, for example, the way we measured the mass of the black hole in the middle of our galaxy, and that was a dynamical technique. Similarly, there are other ways of doing this. Both involve some kind of imaging and in many cases spectroscopy to measure Doppler shifts so that one can find the velocities of the stars in their orbits. There is another technique which is called reverberation mapping, which can directly measure the mass of the black hole in the middle. We are not going to discuss this today, but it is an emerging field. A lot of black hole masses are measured that way. But the other thing that we have to establish, just as we did in the case of our own galaxy, is that we have to establish that the object in the middle of this galaxy cannot be anything else other than a black hole. Measuring the mass is not enough, because clusters of stars often can have similar masses. To do that, as we did in the Milky Way, we can find some way of measuring the size of the central object, or find some kind of an upper limit to the size of the central object. And in many cases, where we are modeling the object from the point of view of their radiation around the object, we can try and establish the absence of a surface. We know the difference between black holes and neutron stars is that black holes don't have a surface that radiates. This is more commonly used in galactic sources, which are stellar mass black holes, but this can be also used for the modeling of these black holes. So these are some of the ways in which these black holes can be established in external galaxies. All of these have been used. A popular method is using the spectra in the X-rays, for example. One can use variability studies in which we can measure the variability of the radiation coming from around a black hole, and that gives you some limit on the size from which this radiation is being emitted. Here's an example of the use of optical spectra to find the mass of a black hole in the middle of a galaxy. So we have emission lines that originate from very near the center of a galaxy, and you have material moving at very high speed around the central black hole, which emits this radiation, and that causes the emission lines to broaden, and they can go up to many thousands of kilometers per second if one goes to radiation that originates from the center, very center of a galaxy. And this can be caused by just the dynamical effects as well as the gravitational effect of the black hole in the middle. Both the Doppler broadening and the gravitational broadening contribute to the broadening of the emission lines, and that gives us a way of measuring the mass of the black hole that is causing it. Another way of doing this is to look at the broadening of the ion K line from X-ray spectra. This gives a very accurate measurement of both the gravitational effect of broadening as well as the speed, the Doppler effect due to the speed of the gas that is in the accretion disk around the black hole, the very hot gas. And so there are many galaxies in which from the X-ray spectra one has measured the central black hole's mass, or even established the existence of the black hole in the middle through the observation of the ion K line. Now, does every galaxy have a supermassive black hole? This is a question often asked, and this was one of the earliest questions that the Hubble Space Telescope had to address when it was launched. And one of the things that was found was that there is an evidence of a compact, massive object in the middle of almost all galaxies, unless they're a real dwarf satellite galaxy that is orbiting a major galaxy. It is true that one can actually show that the central objects are black holes in only the more massive galaxies. So for example, if the mass turns out to be something like 10 to the power 6 times the mass of the Sun or higher, one can establish that it's probably a black hole, a supermassive black hole. There are many galaxies where the central object is much lower, of the order of 10 to the power 4 or 10 to the power 5 times the mass of the Sun, and it is not clear to us whether we can call these black holes. They're probably very massive star clusters in the middle. But it is clear that almost all the massive galaxies have supermassive black holes in the middle. In this plot, they are marked as CMO, central massive object. The massive object is, in these cases, the supermassive black hole. Now, we see a kind of scaling relation between the mass of the supermassive black hole that's found in the middle of a galaxy and the size of the galaxy. Now, it's not the size really that scales with the supermassive black hole mass, but the mass of the bulge of the galaxy. So in this particular plot, the left panel shows the mass of the black hole and the luminosity of the bulge of the galaxy. And this, by bulge, I mean the central spherical part of the galaxy. In the case of a spiral galaxy, that is only part of the galaxy. In the case of an elliptical galaxy, it is the whole galaxy. But the mass of the bulge is the one that correlates with the mass of the supermassive black hole. In this case, it's the luminosity. And in the other plot here, the x-axis is the velocity dispersion of stars in the bulge. That correlates directly with the mass, as you know, of the galaxy. And so that here is a very tight correlation between the mass of the central black hole and the mass of the bulge measured through the velocity dispersion. This is often known as the Megorian relation. We now have measurements of these in many, many nearby galaxies, where the mass is measured by the various methods I talked about, the reverberation mapping method, the dynamical methods, and also looking at the dynamics of the gas that's around the central black hole. The bulge of the galaxy is the one here, for example, that correlates with the mass of the central black hole, not the disk. That tells us something, and the interesting thing here is that the fact that the black hole mass correlates with the velocity dispersion or mass of the bulge is telling us that it is related. The black hole's genesis is related to the genesis of the galaxy. We still don't know how these supermassive black holes grow in the middle of galaxies, whether the galaxies form first and then the supermassive black hole grows in the galaxy, or whether the galaxy itself is seeded by the initial supermassive black hole. Whatever the answer is, we know that there's a relation between the two. Otherwise, the mass of the black hole would not be correlated with the mass of an important part of the galaxy. And so we know that as the galaxy evolves, the galaxy is aware of the fact that the black hole in the middle of the galaxy is growing at a rate that is related to the mass of the central part of the galaxy. Now, galaxies change during their lifetime. They start their life as disk galaxies, and then they're transformed into elliptical early type galaxies where there's very little star formation. There is considerable research going on when and how galaxies change from disk galaxies into the more spherical or elliptical type galaxies. And one of the things that changes quite a bit is their rate of star formation. There's quite a lot more star formation going on when the galaxies are in the form of disks, and later in life their star formation ceases. And in this particular section, we'll look at how galaxies cease to form stars, whether it is a process that is internal to the galaxy or whether it depends on the large-scale environment in which the galaxy sits. In clusters, we find an abundance of early type galaxies, galaxies that are spherical or elliptical, and they're red and they have very little star formation. These dead galaxies have also very little gas or dust, and clearly a transformational process has happened as the galaxies have been assimilated into these clusters and also undergone this transformation. So, this gives us a first clue that the density of the galaxies around a certain galaxy is related to the fact that the galaxies are transformed, because you find more of these galaxies of very little star formation in clusters or in groups than in the field. We see that in the global transformation of star formation. If we look at high redshift galaxies and compare their star formation with galaxies at very low redshift, we find that star formation peaks at about a redshift of 2. At redshifts higher than 2, there is quite a lot of star formation going on in galaxies. This is the star formation rate on the y-axis, redshift on the x-axis. And then nearer the present time at redshift of 0, star formation steadily declines. And the question is, why star formation stops in galaxies? Is it a process that has to do with the various things that are inside the galaxy? Is it something that is related to the normal aging of the galaxy as the gas that goes into the stars is consumed? Or it is a process in which the environment of the galaxy influences what is happening inside the galaxy. This is often also known as the question of nature versus nurture, taking cues from the social sciences, where people look at these questions of whether, say, a human life is related to more the environment in which the person grows up, or changing or aging or maturing is an internal process. We know that both are likely, because we know that it is the change of galaxies related to the populations of stars within them, but also we can see circumstantially that we find early type galaxies more in dense environments. This was first shown by Dressler in the 1980s in a very famous paper, which is known as the morphology density relation, in which what he did was he plotted the frequency of these galaxies that are found in different environments as a plot which shows on the y-axis the relative frequency of these galaxies, and on the x-axis it shows the density, the local density of galaxies around the particular galaxy. And here you can see that as the density, which is plotted in logarithmic form, and the x-axis goes up, the number of spiral or disk type galaxies goes down very steadily, and the number of the elliptical galaxies, which have very little star formation, goes up. The morphology of the galaxy, which tells you just the shape of the galaxy, is related to what is going on inside the galaxy, and is also related to where the galaxy lives. We can look at the various physical processes that we know now that transform galaxies. We know a lot of these from theory. Also, early simulations done in the 1970s, 80s and 90s showed us that if you consider the dark matter component of the galaxy and the stars and the dust and the gas that's in the galaxy, how they will change as they age and also as they interact with each other. And we are going to go through the three most important processes that transform these galaxies to show that the transformation of galaxies is related to nature and nurture both. Let us look at ram pressure stripping. This is what happens when a galaxy moves through a medium which is gaseous. This might be in a group or a cluster in which the gas is in between the galaxies, and a galaxy, as it moves in the dark matter potential of the cluster, also moves through this medium. And what would happen is that the intergalactic medium, which is the gas, which could be in the form of mostly cold gas, but it could be, in the case of very heavy clusters, it could be in the form of hot gas as well, would then take the gas out of the galaxy. The cold gas in the galaxy would be stripped off as the galaxy moves through the cluster, and this is known as ram pressure stripping. There have been nice simulations done, hydrodynamic simulations, that show how this happens, what time scales these happen, and in actual observations you can see, for example, here the H1 contours, the radio contours of cold gas from a galaxy, which is shown, the optical picture of it is shown underlying the picture, how it can be stripped off as this galaxy moves through a cluster in that direction. We also can have this when galaxies interact very closely. Often we use anthropomorphic terms like collisions, harassment. Galaxies can harass each other, and in this case what is happening is that due to the close interaction between these two galaxies, which are not quite merging but interacting through tidal means, one galaxy can cause gas to escape from the other, and it can be pulled out of another galaxy in the form of streams. Here are some simulations that can show this to happen. Nearby interacting galaxies, we actually see this happening in many galaxies. We call this harassment because this can often happen for a giant galaxy to cause the gas to be stripped off dwarf galaxies, smaller galaxies that orbit these giant galaxies. What happens in this case is that as the galaxy loses the cold gas, it also loses the fuel for star formation, and as a result the star formation of this galaxy can stop. And the third one also is a term that sounds very anthropomorphic, and that is triangulation, which means that galaxies in general, the galaxies in a group or a cluster, can cause the star formation in a galaxy to be strangulated, and in this particular case by getting rid of again the source of the star formation. And in this particular case what happens is that a galaxy which has normally a reservoir of cold gas around it, in the form of a halo around the disk galaxy, and this cold gas falls into the disk slowly in order to fuel the star formation that is going on in a disk galaxy. This reservoir of cold gas has been detected in very sensitive radio observations, and as these galaxies interact with other galaxies closely in a group or a cluster, what can happen is that the reservoir of cold gas that is shown here is stripped off the galaxy, and that strangulates the star formation within the galaxy. This can be shown in wonderful simulations done by Lars Hörnqvist and collaborators, for example, and now it has been shown to happen in galaxies that exist in groups or clusters.